Does anybody want to look at anything from any homework, either leftover chapter 5 stuff or new chapter 6 stuff? Mackenzie and Sam, got to change attendance. Give me a second, folks. But you can look and see if you have questions before we do that. Does anybody have any homework questions from any of the chapters that they want to look at? No?
I feel free when the morning glimpse of nature fell all over my body, trying to enhance my features, trying to playfully tease me, trying to make me more optimistic about life, trying to admire even every single flower. Yeah.
Okay. Anybody want to look at any homeworks?
Hi, I'm here. I just didn't hear my name called because it wouldn't let me log in for a second.
I got you, hon.
Okay, thank you.
All right. If not, I have that we left off looking at getting expressing fractions with common denominators, which is going to lead to adding and subtracting fractions. And so before we started looking at the computation involved with adding and subtracting fractions, I thought we could go back and look at those activities that we had not yet done. The activity 7 and activity 9. One dealing with adding and subtracting fractions, and the other dealing with multiplying and dividing fractions. So when they use the pattern blocks for fractions, you determine that one of them represents the whole number 1. And so in the first side of this sheet, they're saying that give me a second. They're saying that the yellow block is the yellow hexagon is the number 1. And so then the red trapezoid is a half, the blue rhombus is a third, and the green triangle is a sixth. Can you folks, do you folks have your pattern blocks out with you? Starting with having the hexagon be 1. And so they're saying if the hexagon is 1, the trapezoid is a half. And I think here you could see the 2 trapezoids would make the hexagon. They're saying that the rhombus is a third because if we move them just right, we can see that it takes 3 rhombuses to make the hexagon. And then the green triangle is a sixth. And I think everybody can picture it taking 6 triangles to go around and fill in the hexagon. And so they're saying, well, if I add 1 red plus 3 green, 1 red would be a half. And then if I look at 3 green, let's move everything else out of the way. 1, 2. And this would be easier if we were actually working with them. I apologize. I'm not real good with manipulating the virtual ones. 3 greens. Well, they're saying, well, now wait a minute. Aren't the 3 greens equivalent to 1 red? And so that we could say that that would be like 1 red plus 1 red. Or we could also say that it's like 3 green plus 3 green, which would give me, when I add them together, I could say that adds up to 1 yellow, which would be the number 1. And right now, the stylus is stopping. So in that same way, if you would take out your pattern blocks and look at the next sum, which is 1 red plus 1 blue. And so if we're taking 1 red and adding to it 1 blue, well, then they're saying, okay, 1 red is equal to how many greens? Oh, and I think down here we have it that 1 red is 3 green. And that would be 3, 6. And 1 blue, if we go back and look at the pattern blocks, 1 blue, well, wouldn't that be equivalent to if I could manipulate these things, 2 greens. So that would be 2, 6. And so when I add them, I would get 5, 6, which would be 5 green. And so in the same way, if you were to add 1 blue and 1 green, what would that turn out to be? What would you say that 1 blue is equivalent to?
2, 6, or 2 triangles.
Yeah, or 2, they're determining them by color. So we'll say that 1 blue is 2 green, which would be 2, 6 plus 1 green, which would be 1, 6. And so when I add them, I would get 3, 6 or 3 green. And then if we look at the 3 green would be equivalent to
1/2.
1/2 or 1 red. And so we could take more time going through and looking at this, but you see how we can use the pattern blocks to kind of show the relationships between getting those equivalent denominators so that we can, common denominators, so that we can add those fractions. That page all right? That the next page is a similar idea, but this time they're saying that 2 yellow hexagons make a whole. So 1 yellow hexagon would be a half. That red trapezoid would be a quarter. The blue rhombus would be a 1/6, and the green triangle would be a 12. So if you were to use your pattern pieces and add them, 1/2, that yellow hexagon, well, how many 12ths would that be? how many green triangles would it take to fill that yellow hexagon?
6.
So we could say that's 1/2 plus 3/12 is 6/12 plus 3/12. And so when we add that, we would get 9/12. And now let's see, how could we think of that as expressing it in lowest terms? I'm going to backtrack a little bit. What we were doing was we were adding 1/2 and 3/12. Well, if we wanted to show that as the smallest number possible of ones that are the same color, wouldn't that be equivalent to 3 of the red trapezoids? And so using that equivalence, wouldn't that give us 3/4? And again, that same general idea of using the different colors and shapes and filling in to show the idea of getting that equivalent denominator. I find these ones interesting because, again, I think I told you folks last class that I once had one of the people in the biology department come running to me because they couldn't understand their child's homework, and it was because it was using these pattern blocks to do fraction manipulation, where they used the 2 hexagons to equal a whole. And I think last time we also looked at the idea of using those fraction strips in order to show addition. And so here, if we were to take 1/3 plus 1/4, when we line them up, we'd see that the sum would be equivalent to, on that 12th strip, 7/12. And in the same way with subtraction, we could look at it almost more like the missing addend model. I have 2/3, and then I have 1/4. What would I need to fill in here? What would I need to add on to get the same length? And so we need to add on 5/12. And so, again, I have to apologize. I'm not real great with these virtual manipulatives, but I did find a version of the fraction strips. So using these fraction strips, if I wanted to take 1/2 and add to it 3/5, we have to figure out what I could show that being equivalent to with the other strips. And so I do believe that it would line up with the tenths to get the same length. And so that would give us 11/10. And in the same way, if we just try to look at one more, if we look at that 7/8, so 7/8, we'd have 7 of these. And ideally, I'd be able to line up the 1/4 at the end, but this doesn't let me. And so over here, in order to figure what I would need to complete that, 7/8 plus, well, I think we'd have to fill that in with 5/8 to get that same length. And so that answer would be 5/8. And again, just another hands-on way of looking at that idea of adding and subtracting fractions. So then the next question becomes, do you folks have your activity manuals and your fraction strips and things with you? Is it worth time right now to stop and have you folks try some of those on your own? Or do you not have them? So talk to me, people. Are you guys doing a couple of these on your own now or not? Should we do the breakout room thing again? Or if enough people don't have the manual and the manipulatives with them, is this enough of an example to give you guys an idea as to how this would work? Do you guys want to do it? Yes or no? Nobody's answering. All right, if you're not going to answer, I'm going to go on the assumption that you don't want to play with your manipulatives tonight, or you do. Nabby, what do you think? Courtney, what do you think? Egypt.
I don't mind.
You don't mind?
No, I don't mind either way.
You don't mind either way? Stephanie? Rachel?
I don't mind either way either.
No? All right. Well, it doesn't sound like anybody's anxious to do it. So let's just take a real quick peruse then at that other activity, because it's sort of neat too. And, you know, I never started. No, I did. The other activity is on dividing fractions. And this one's sort of cool because they're saying, all right, I'm going to say that my 2 hexagons is a whole. And if I take 1 and divide it by a half, what I'm wondering is how many halves would it take to fill in that 1? And so does everybody see that this one would be made up of 2 halves? So 1 divided by a half would be 2. And so if I were to, with the, let's look at number 2, if I wanted to take a half divided by a 4th, well, that would mean a half was the hexagon. And the 4th was that trapezoid. And so we're asking how many trapezoids does it take to fill in the hexagon? And wouldn't that be 2? Because if I took my hexagon, I would be able to fill it in with 2 trapezoids. And again, just another way of looking at that idea of division of fractions using those manipulatives. So those pattern blocks get used a lot. And so then skipping on to the next page, if we look at this example, they want to take a half and divide it by a 1/3. And they're using the idea that it takes 2 rhombuses to make a 1/3. Well, when I take that half, I can fill 1/3 in there. So there's 1 whole. And then this piece here, wouldn't this piece be a half of that 1/3? And so we'd say that that quotient would be 1.5. And so again, that idea of when I divide it, I'm asking how many of these can I put in there? How many of these can I fill in the space with? So, which is, again, I think a different approach to division of fraction. Much different than the way in which I learned it, for sure. We didn't really use manipulatives very much back in the Stone Ages. And I think it's also much different than what I had seen my children learn. How about you guys? Did any of you learn your operations on fractions this way using things like these pattern blocks? Did any of you see that in elementary school? No? No. I know, though, they have to be using it because my coworker was like in a tizzy about it. I don't know if it's part of that Common Core approach or not. So if you get a chance, look at those activities and use your pattern box and see how you can work with them. All right. So that having been said, any questions? Any thoughts? What do you think of that idea of using the different shapes and the different length strips as manipulatives to learn about fractions?
I think it would have been easier to learn it that way when I was a kid than the way like we did learn it or were taught.
Uh-huh.
I feel like kids now are going to grasp this better because it's more hands-on.
Okay. All right. All right. Very cool. Anybody else have an idea? Egypt, I love your company.
I actually agree. I think if I learned it that way, it would have been easier.
You think so? Okay. All right. Do any of you do any work like with after school programs or anything like that outside of school, working with children? Although I guess right now in the time of COVID, they probably discourage that. Have you guys been able to do any sort of placements with your EDU classes, or because of COVID rules are kind of keeping folks out of those elementary schools? Have you been going in or not? No. All right. Well, hopefully, before you finish your careers at the community college, all of this will be over. Let's hope it's all over by the springtime, right? And you can do a little bit of actually working with in the elementary classrooms and seeing how they use this. So, all right, then let's go back and share again. And I think we had left off on page 6 of the notes, where we looked at that idea of getting a common denominator and then using the common denominator to order fractions greater than or less than. Does everybody remember where we were? Did anybody have questions on any of that? If not, then the next place we're going to go is something that's called the density property. And the density property says that if R and S are rational numbers, and does everybody remember rational numbers is just a fancy way of saying a number that can be written as a fraction? So we've got two fractions, and we'll say that R is less than S. Then there always exists a rational number T such that R is less than T is less than S. Or we could say that if A over B is less than C over D, then there exists an E over F such that A over B is less than E over F is less than C over D. Or just the general idea that whenever I have any two fractions, I can always find another fraction whose value is in between them. So there is always a fraction between two fractions. And then let's stop and think about that idea. Well, if R is less than S, we can put a T in between them. But now R is less than T, so we put another one in between them? And then can't we put another one in between them? And can't we put a number one in between them? And so actually, this leads to the idea that there is an infinite number of fractions between any two rational numbers. Or there is an infinite number of rational numbers between any two rational numbers. And that idea that we can keep stuffing more and more in between is what makes that idea of them being dense. So let's say, for example, we know that 4/5 is less than 5/6. We want to find a rational number between them. So, how can we do that? How can we find a number that we would be midway between them? Any ideas? Any suggestions? What if we first express them with a common denominator? So between denominator 5 and 6, what would you think that we could use for a common denominator? Any ideas? Couldn't we always use 5 times 6 or 30? And so where I have that 4/5, if I might multiply numerator and denominator by 6, that would be 24 over 30. And if I have that 5/6, if I multiply numerator and denominator by 5, that would be 24 over 30 is less than 25 over 30. But I still can't fit anything in between them. Now, maybe if we express them with a larger denominator, if we multiply this by 2 over 2, That would give me 48 over 60. And if we multiply this by 2 over 2, that would give me 50 over 60. And so what fraction could we put in between 48 over 60 and 50 over 60? Any ideas? Couldn't we fill that space in with 49 over 60? And so we were able to find a fraction in between the two by expressing them with a common denominator. A lot of times just getting that common denominator will leave a gap in the numerators. But if it doesn't, multiply numerator and denominators by the same value so that you can find a fraction in between. How's that? All right? And again, that's one property that's special to these rational numbers that didn't apply to any of our other number sets. Did they? Did it? And so after we look at that density property, the next place that the author goes in the textbook is the idea of addition and subtraction of rational numbers. And so if they have a common denominator, let's say I have 2/5 plus 1/5. If they have a common denominator, how do I add those fractions? Can anybody remember?
Add the numerator.
I'm sorry, I only heard half of what you said, hon.
Just add the numerators.
Just add the numerators and keep the denominator? And so in general, if I have A over B plus C over B, that'll add to A plus C over B. And we can show this numerous ways with our manipulatives. One way would be with an area model. And so with that area model, I could look at something like, let's look at our hexagon. And so let's look at, let's say, 1/6 plus, let's say 4/6. And so I would have 1/6. And I'd add to it 4/6. And when I combine them, what did I have? 4/6 and the one more, a total of 5/6. Or with an area model, if I were to look at, let's say, 1/8 plus 5/8, let's see, to get 1/8, let me take a square, cut it in quarters, and then add those diagonals. And so that would be like a tray of eighths. And again, in order for this to work, my two squares need to be the same size. But I would have 1/8, and then I might want to add it to 1, 2, 3, 4, 5/8. And when I think of arranging them all together, I have the 5 and add one more in there. That would give me 6/8. And then if I wanted to put it into simplest form, that would be 3/4. And I could take it as looking at 3 of the 4 quarters of my square. And has everybody seen adding fractions in that way? Putting like little pieces of pie in there, so to speak. So far, so good?
Yes.
Then another way of adding them is on a number line. I'm going to move this number line up a little bit. And so let's say with the number line, I want to add 3/8 plus 2/8. And so on my number line, I'd want to divide it into eighths. This would be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and then I'd have 1/8. We said when we add, we're going to start at 0. I'm going to have an arrow of length 3/8. And remember, when we add, we draw them head to tail, so the next tail comes off of there with a length of 2/8, and that would give us a total of 5/8. And then we could also show addition with those fraction strips. With the fraction strips, I'm going to go out on a limb and try adding fractions with different denominators. So if I wanted to take 1/4 plus 1/3, well, for 1/4, if this is my unit 1, this would be my 1/4. And then I'm going to put another strip next to it and have it divided into thirds. This would be my 1/3. And then underneath, I'd have another strip where I would look for something that would match up here. And it would be 1/4 would be 3/12. 1/3 would be 4/12. And so we'd say that it would be equivalent to 7/12. And you would have to compare your strips until you found a sum that matched right at that edge. And I have to apologize. You can see from these diagrams why I teach math and not art. But I think that as we look at the activity, I think that activity 6.7 and using the strips there gives you a better idea of where all of this fits in. Also, I think if you read the textbook, their diagrams are ever so much better than my drawings. So, but can everybody see lining up those strips until we get one where it meets at that edge? Let's see if I go over here to our generic fraction strips. We could see that 1/3 would be equivalent to the 12ths. And we could see that 1/4 is equivalent to the 12ths. So it would make sense that that sum would also be equivalent to something with that denominator. Does everybody see, looking at this lineup, that 1/3 would be 4/12 and 1/4 would be 3/12, and the 12ths would be the first place where they would be in common. So far, so good. If so, when we look at subtraction with rational numbers, we can look at a couple of different models. One model would be the takeaway model. And so let's say I have 7/6 minus 2/6. And if I wanted to show this with an area model to show 6, I might use my hexagons. But over here, because I have more than 6/6, I'd have to have a second hexagon. And so 7/6, let's see, maybe if I use the highlighter, it'll color it in a little bit better. 1, 2, 3, 4, 5, 6, 7/6. And then I want to take away 2/6. And so we can use arrow showing that we're taking those two out. And then when I take them out, if I look to see what remains, I would have 1, 2, 3, 4, 5, 6. In addition to that takeaway model with shapes, area model, we could use a missing addend model. For subtraction using the strips. And so, for example, if I wanted to look at 5/6 minus 2/6, well, if that's my strip, and this would be my 5/6. And then if I want to take away 2/6, I would put another strip here. And take away 2/6. And when I look to see what I would need on my 6th strip to fill it in, the missing add-in would be 3/6, which then we could look at comparing to other strips to see that it's equivalent to 1/2. And then that other model that we could have for subtraction is that number line model. Remembering that on the number line to show subtraction, we draw the arrows head to head. And so, for example, if I were to look for 5/8 minus 3/8 on my number line, this would be 2/8, 4/8, 6/8, 8/8, and with my sloppy penmanship, I don't really think I could neatly write in all of those numbers. So first I'd have my arrow for 5 with a length of 5/8. And using that each of these spaces is an eighth, to show subtraction again, we draw another arrow head to head, whose length is 3/8. And we'd see that that difference would be my 2/8. So far, so good. Any questions on any of those representations? Are we good? If so, then, oops. Let me go back and share my screen. Next place that we go then is to look at subtracting fractions with an unlike denominator. And in one way, adding or subtracting with an unlike denominator, I apologize. If I have A over B plus C over D, we'd want to express with a common denominator. Which could be BD. And so I'd have to multiply this first fraction by D over D. And that would give me AB in the numerator. The second fraction, I'd have to multiply by B over B. So that would give me CB in the numerator. And we'd have that common denominator of BD. In the same way, if I had A over B minus C over D, that would give me AB minus CB over BD. And then, of course, with either one of those, you would reduce it if possible. So let's look at some examples. Let's look at two fifths plus 1/3. And so again, we'd want that common denominator, which would be 5 times 3, or 15. And so if we think of taking this first fraction and multiplying it by 3/3, and that second fraction, multiplying it by 5/5, we have 6/15 plus 5/15, which would give us 11/15. So I'm going to ask you folks to please carefully work out for me, showing all your work. 3/4 plus 5/6. And then in addition, we want to add 2/3. So let me know what you get when you're done. Did anybody else get 9/4 as their final answer?
I did.
Good. Anybody have a question on getting there? If not, draw a little dividing line here because I wrote a little bit too big. How many of you have heard of a proper fraction? What does it take for a fraction to be proper? A over B is a proper fraction. What? Is 2/3 proper? Is 75 over 20 proper? Can anybody remember? One is and one isn't.
Isn't the bottom one proper?
The bottom one is improper. The 2/3 is proper. A fraction is proper if 0 is less than A is less than B. But we're going to get a little bit technical because we had allowed for the possibility of signed numbers here. So we'll say 0 is less than the absolute value of A, which would have to be less than the absolute value of B. And so this is proper, and this one is improper. And can you remember trying to convert an improper fraction into a mixed number being a number of the form A plus B over C, which sometimes you see just written as AB over C. And we could change that into an improper fraction by taking A times C and adding B to it, putting it over C. And so over here, where I have the improper fraction, (75 over 20), if I asked you to express it as a mixed number, can anybody remember how to do that? How to take that 75 over 20 and rewrite it as a mixed number? Remember taking that numerator and dividing it by the denominator, which would give us a quotient of 3 and a remainder of 15. So 75 over 20 would be 3 and 15/20. And you could express your remainder as a fraction. And then that one we could even simplify further, dividing both numerator and denominator by 5 to get 3 and 3/4. And in the same way, I might ask you to, actually let me go to the top of the next page instead of writing down here below the paper. I might ask you to express as an improper fraction something like 2 and 3/11. And so in order to do that, I would have to take that 2 and multiply it by 11, thinking of multiplying it by 11 over 11 and adding the 3. So that would be 22 plus 3 over 11, or 25/11. Does that process look vaguely familiar, folks? I think that as you got older and your mathematical skills became more sophisticated, you realized that a lot of times it was difficult to show mixed numbers with signed numbers. You have to be careful with your signs. If I have -3 and 2/3, that means the negative of 3 plus 2/3, which, let's see, 3 times 3 is 9 plus 2, and that's -11/3. This is not -3 plus +2/3. That 2/3, the way this is written as a mixed number, it's all negative. And then one place where working with improper fractions becomes important is to subtract mixed numbers. The other option, if you didn't want to work with improper fractions, subtracting mixed numbers, is to do borrowing or exchanging like we did. But most folks find it easier. If I were to have something 4 1/3 minus 2 3/4, to do a subtraction like that, I want to rewrite these as improper fractions. So let's see, 4 times 3 is 12, plus 1 is 13/3, minus 2 times 4 is 8, plus 3 is 11/4. Then I'd want to get my common denominator, which would be 12. So this one I have to multiply numerator and denominator by 4 to get 52/12. And the second fraction would multiply numerator and denominator by 3 to get 33/12. And then we worked hard to get that common denominator, so we'll keep it. And then subtracting the numerators, 52 minus 33, it's a little bit less than 20 away, would be 19/12. And then we'd, rewrite again as our mixed number. Or the idea that 19 divided by 12, 12 goes into 19 once, leaving us with a remainder of 7, giving us 1 and 7 twelfths. So, can I get a pause for a minute and look at you folks? That level of arithmetic with fractions, is it something that you can recall doing? Are you comfortable with it? Are you proficient with it? What do you folks think? Is life good? Yep. People who are responding are nodding. Otherwise, they're giving me that blank stare. I hope that blank stare doesn't mean that anybody's fallen asleep. But if that's all right, then let's go on and look at multiplication of and division of rational numbers. And when I look at multiplying by a whole number, we can show that with repeated addition. So for example, if I have 3 times 1/8, that would be 1/8 plus 1/8 plus 1/8, or I'd be adding 3 of them together, and that would give me 3/8. I could do that with a circle model. If I had, let's say, 2 times 1/5, I could look at that as 1/5 plus 1/5. And when I put them together, I would have 2/5. I could look at it with the strips. So this circle model would be my area model. If I had 3 times 1/4, I could look at my strips for 1/4 plus 1/4 plus 1/4, and that would give me 3/4. Or I could look on a number line. And I could look at -3 times 1/7. You know what? I'm going to change that to 1/8 because it's easier to draw 8s on a number line. And if you remember correctly, if we were looking at multiplying by a negative on the number line, we would be looking at it as taking away. And so I would have 1/8, 1/8, 1/8, and that would take me to -3/8. Instead, if I wanted to look at multiplying a fraction by a fraction, this is where I think an area model is a great way of showing it. Let's say I wanted to take 1/2 times 1/3. I'm going to look at having a square or a rectangle. And on one side, I'm going to think of dividing it in half. So this would be 1/2. And then on the other side, I want to think of dividing it into thirds. And so this would be 1/3. And if I look at the full square as a whole, is it obvious that this product this piece that's got dimensions 1/2 by 1/3 would be 1/6. Instead, if I wanted to show 3/4 times 2/3, again, I'll start with this unit square. And one side I divide into fourths. And so let me use my highlighter here. This would represent 3/4. And then the other side, I would divide into thirds. And with a different shade, I would shade in 2/3. And if I look for the overlap, this piece that's 3/4 by 2/3, well, inside there, I would have 6 of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 squares. And then we could realize that 6/12 would reduce to 1/2. And do you see how dividing one fraction on one side of the square and the other fraction on the other side, and looking for the product as being the area of the overlapping regions, can lead to this idea of how we multiply fractions? Or that rule for multiplying fraction would be if I have A over B times C over D, I'm going to multiply across. It's the product of the numerators over the product of the denominators. And then we reduce. And so we were able to show it quite clearly that if one side's divided into fourths and the other side's divided into thirds, it's obvious that I have 12 blocks and they would have in common 6 of them. Otherwise, I would have 3/4 times 2/3 would multiplying across give me, let's show that middle step, 3 times 2 over 4 times 3, which would give me 6/12, which I can reduce to then 1/2. Or you can reduce as you go. I think this was kind of back in ancient times. We called this idea cross canceling. When I have that 3/4 times 2/3, or if I have that 3 times 2 over 4 times 3, especially when I teach this in an algebra class where we're doing this with variables and not numbers. Is everybody familiar with that idea that you can cancel out a factor common to the numerator and denominator? And so even before I multiply, I can divide those 3's. 3 divided by 3 is 1. 3 divided by 3 is 1. And I can also divide 2 divided by 2 is 1. And then 2 goes into 4 twice. And that leaves me with the 1/2. How do you folks feel about that canceling as you go? Are you more comfortable cross canceling, or are you more comfortable multiplying and then reducing?
I prefer the multiplying and then reducing.
Okay, all right. So this multiplication, I'm going to kind of scooch way over here, is also another place where you might want to use improper fractions. Instead of mixed numbers. To multiply. So for example, if I have 3 1/7 times 5 1/4, I would take that mixed number 3 1/7 and again change it into an improper fraction. 3 times the 7 would be 21, plus the 1 is 22/7. And then here, 5 times the 4 is 20, plus the 1 is 21/4. And now with this one, we could just multiply across and reduce. But as I start looking at products like 22 times 21 and trying to reduce the fraction, let's see, if I have 21 times 22, I have 462 over 28. And then I think in order to, I'm going to erase my scrap paper because I'm running out of room here. I apologize. Reduce that, which might be kind of tedious to do. Instead, But I have that 22 over 7 times 21 over 4. Can everybody recognize that 7 divides into 21 evenly? So 7 into 7 is once. 7 into 21 is 3. And then along the other diagonal, 4 and 22 are both even. 4 divided by 2 is 2. 22 divided by 2 is 11. And so then when I multiply, 11 times 3 is 33. Over 1 times 2 is 2. And then simplifying, 2 into 33 would be 16 with a remainder of 1. I guess looking at it working backwards in order to get to this result, we would have needed to recognize that I can divide both the numerator and the denominator by 14 to get it to reduce down this far. And so I guess, well, if you didn't see that, would you have divided out 2 here to get 231 over 14? And then we couldn't divide by 2 anymore, but we'd have to recognize that we could divide both of those by 7 to get that 33 over 2. So sometimes it's a little bit more cumbersome if you wait until after you multiply to reduce. So how was that? Any questions? If not, from the textbook, I pulled out a couple of interesting word problems that involve this idea of multiplication with fractions. And so we've got a, oh, that shouldn't be Ling, that should be long, shouldn't it? Sorry about that. We've got this hallway that's 5 feet by 15 feet, and we want to carpet it. But we know the cost of our carpet in square yards. And so I think in order to find this price, we'd have to try to think of those feet as yards. So I guess the $1 million question right now is, can anybody remember how many feet are in a yard? Anybody remember?
3.
Yep. So 1 yard is 3 feet. And so over here, couldn't I say that 5 feet is 5/3 of a yard, or 1 2/3 yard? And in the same way, that 15 feet would be 15/3 of a yard. And so that area, 5 feet by 15 feet, would be 5/3 of a yard times 15/3 of a yard. And is there anybody else that would want to take that 15/3 and reduce it? How would 15 over 3 reduce?
Three over one.
I agree with that the denominator is 1, but in order to get 1, we'd have to divide that 3 by 3. And so if I divide that numerator by 3, are you all right? Instead of 3 over 1, it would give me 5 over 1. And so that would give me 25 over 3 square yards. And so to find the cost then, we'd have to take that 25 over 3 square yards and multiply it by $20 for each square yard, which would give me, let's see, I'll do the hard part. I think of that as 20 over 1, I get that denominator. 25 times 20 would be 500. And so if I take that $500 and divide it by the 3, let's see, 3 into 5 once, 3 into 26, 3 into 26. Oh, and I think it's just going to keep on dividing. And so we'd say it would cost approximately $166.67. Thoughts? That level of work look real doable to you folks? Should we try another slightly different one? This one, we're looking at a map, and on our map, the scale tells us that 1 inch is 2.5 miles. On the map, two cities, Mathville and Fractionville, are 3.5 inches apart. How far apart are they in miles? Well, let's see. I have 3 3/4 inches, and each inch is 2.5 miles. And so I think we need to multiply. And so I'm going to be quiet for a minute and ask you folks to please find this product for me. Tell me what you got. Did anybody else get 9 3/8 smiles?
Yes.
Yes? All right.
Yes.
Everybody comfortable with that? I am going to, if you don't mind, after I just need to take like a 2-minute break to run downstairs and get a glass of water because my throat is scratchy. So should we just as a whole take a 5-minute break, let everybody get up and stretch their legs for a minute and be right back? All right. So we'll see you all in about 5 minutes. This is one of those days where I'm going through halls by the bagful. Let me see. I think a couple of people came in that weren't here during attendance. Is everybody back or should we wait another minute? I think Naomi had her camera on, so let's give another minute. So next we go on to the idea of the division of fractions. And with the division of fractions, we can look at it in a couple of ways. And one way is almost like a area type model. And so if I were to take 2 and divide it by a half, that would actually be asking me how many halves are in 2. And so we could look at this in the same way we did with that opening activity, so that if this box is my unit 1, I could look at that as saying that there are 4 halves in there. And so 2 divided by a half would equal 4. And we looked at that a little bit in that activity for chapter 6, section 9. And we'll look at some word problems in a little bit that ask us to take that perspective. Actually, you know what? Let's go ahead and look at those problems first, and then go back and look at that more formal definition. And so over here, if I have 2 3/4, and I want to divide it by a half, I could ask how many halves are in 2 3/4. And so here, let's use the block to equal 1. And so I'd have 2, and then I have 3/4. And then I wonder how many halves are in there. Do you see how we have 1, 2, 3, 4, 5 halves? And then wouldn't this piece be half of a half? So we would say that that is 5 1/2. Likewise, that same type of spatial model, I could say that I have 2 1/2 acres. So this would be 1, this would be 2. And then I'd have a half. And I want to seed it, but I know that each bag of seed covers 3/4 of an acre. So here, this would be 1 bag, 3/4. Then this combined with this would be another bag, 3/4. So that's 1 bag. These would make a second bag. And then let's see, these two with half of this would make a third bag. And so I'd need 3 whole bags, and that would be 3/4. That would be 3/4. That would be 3/4. And so up here, this would be a fraction of a bag. And wouldn't that be, if a whole bag covers 3/4 of an acre, I just have 1/4 left, wouldn't that be a third of a bag? And so my answer would be 3 1/3, or I guess we could think of that as 10/3. And again, that's real similar to what we were doing with those pattern blocks, pardon me, in the activity, asking how many 3/4 would it take to fill that whole area. Instead, I could look at a more formal definition of division. And in a more formal definition of division, we had first said that if I had A divided by B equals C, that means that A is equal to B times C. And so with rational numbers, if I have A over B divided by C over D is equal to some fraction M over N, we would say that that means that the dividend is equal to the quotient times the divisor. And now here, we want to introduce the idea of the reciprocal of the fraction. And to get the reciprocal of a fraction, I interchange the numerator and the denominator, always being sure that we can never have a 0 denominator. So the reciprocal of A over B is B over A. And if I look at the product of a rational and its reciprocal, if I have A over B times B over A, that would multiply to AB over AB, which is 1. And so the product will always be 1. Again, making sure that I'm not multiplying by a 0 denominator. And so if I go back to A over B divided by C over D equals M over N, meaning that A over B is equal to M over N times C over D. We're going to say to find the value of M over N, we can multiply both sides of that second equation by the reciprocal D over C. So that would give me A over B times D over C is equal to M over N times C over D times D over C, which gives me that quotient M over N is equal to A over B times C over D. Or if we put all of the pieces together, A over B divided by C over D is equal to that M over N, which is equal to A over B times D over C. Getting out the middleman, A over B divided by C over D is equal to A over B times D over C. Or has anybody ever heard that keep, change, flip, or to divide by a fraction? You multiply by its reciprocal. So, what's that all about? I'm going to backtrack for a minute. And so, here, when we had 2 divided by a half, that whole number 2, we could think of as 2 over 1 divided by a half. And to divide by a fraction, we'll multiply by its reciprocal, which would have taken me to that 4, without pulling out all the squares and trying to see how many halves I have in 2 wholes. Likewise, when we looked at 2 3/4 divided by a half, well, again, we want to take that mixed number and change it into an improper fraction first. Let's see. 2 times 4 is 8 plus 3 is 11 fourths divided by 1/2. We keep the dividend. We take the reciprocal of the divisor. We multiply. And then we can reduce and change it back into a mixed number. And so using this algorithm for dividing fractions to multiply by the reciprocal takes us to the same place as seeing how many half a square we can fit into 2 2 3/4 squares. Or likewise with the bag of seeds, we had 2.5 acres and we wanted to see how many 3/4 were in there. So let's see, 2 times 2 is 4, plus 1 is 5/2 divided by 3/4. And then to divide, we'll multiply by the reciprocal, which would give me 26. 6 goes into 23 times with a remainder of 2. And that reduces to 3 1/3. And we get that same result that we had gotten, seeing how many 3/4 shapes we could pull out of that 2.5. So to divide by a fraction, we can look at using manipulative tips, how many blocks go in there type of thing, or using that definition of a reciprocal, we can show that we're going to divide by the reciprocal. And so, looking at some more examples, I'm going to ask you folks to please take 3/4 and divide it by 1/8. I'm going to ask you to take 1/8 and divide it by 3/4. I'm going to ask you to take 2/5 and divide it by 2/3. I'm going to ask you to take 3 and divide it by 3/4. And let's see if we can fit one more in here. 4 1/6 divided by 2 1/3. And I'm going to give you folks a few minutes to work those out. How are you folks doing? How did you folks do? Any questions? Does anybody need a slow-mo instant replay on any of them? Any questions? If not, then what's left in chapter 6, just like when we finished with the whole numbers, we talked about properties. When we finished with the integers, we talked about properties. When we finished with the rational numbers, we want to talk about properties of rational numbers. And the first property that we want to discuss is that they're closed. They have closure under addition. We had shown that if we add any two general rational numbers, we would get the sum, which is also a rational number. We'll find that the commutative property of addition holds. The associative property of addition holds. You'll see that 0 is our additive identity. And it is a rational number because we can think of it as the ratio of 0/1. And we're also going to see that we have our additive inverses. It would be A/B, and the opposite of A/B that would add to give me 0. And so we have all of those properties for addition. Then we can define subtraction. Also is adding the inverse. Which was one of our integer properties. If I have A over B minus C over D, I can think of that as A over B plus the opposite of C over D. Then we have property for multiplication. Multiplication has closure property. If I have two rational numbers, A over B times C over D, their product can also be expressed as the ratio of integers. Multiplication will be commutative. Because the integers that make up the numerator and denominator have that commutative property of multiplication. Multiplication can be associative. And then we can say that multiplication distributes over addition. The zero multiplication property will hold true. Where if I have 0 times any rational number, it will equal 0. We have that 1 is the multiplicative identity. And that if I take 1 times A over B, I can think of that as 1 over 1 times A over B. That will also leave me with that factor I started with A over B. And then we get the idea that our reciprocals are our multiplicative inverses. Which exists for all numbers except 0. That if I have A over B, when I multiply by B over A, I get AB over AB, which is 1. And I get my identity back. But again, A cannot equal 0, nor can B be 0. We can add the property of density, what we started with today, the idea that between any two rational numbers, there exists at least one rational number. And that idea of putting one between the next two, takes us to the idea that there's an infinite number of numbers in between. And it leads us to the ideas of order, that trichotomy postulate, that A is less than B, or B is less than A, or A equals B. Only one is true. We have a transitive property of order. Which says that if A is less than B and B is less than C, then we can conclude that A is less than C. So lots and lots of properties. And you'll find that many of those properties of rational numbers can be used to develop pretty much from those basic properties and anything with math at any level. All of your rules for algebra, all of your rules for even calculus can be traced back to these basic properties. So that takes us to the end of chapter 6. I didn't ask you guys to prepare for chapter 7 activities, and so I'm going to ask you for the next class to make sure you have your activity manuals and the punch out manipulative. We'll start working on chapter 7, finish that up, and then we'll soon after have test 4. We'll see how long it takes us to go through chapter 7. Test 4 will be on chapters 6 and 7. And then the final exam will be made of questions from the previous test. Just the numbers might be changed to protect the innocent. So they won't be exactly the same questions, but they'll be pretty gosh darn close. I know we're about a half hour early, but am I correct in assuming that at 8:15 at night, you guys are just about hitting math overload? Yep. Does anybody have questions on anything that we've looked at? Gonna backtrack 1 minute. Go back to that screen share. Sorry, I didn't mean to disappoint you and tell you you're all ready to go, but I'm just thinking, want to make sure that everybody's aware that these questions won't be due next Monday, but the following, which is December 12th. But I would strongly suggest you try to complete by Monday, so that if you have any questions on them, we'll answer questions on those first before we start chapter 7. In chapter 7, we're going to find deals with our decimal numbers, and it'll actually lead us a little bit of an introduction to that idea of that next number set, which are the real numbers. So, any questions?
What day is the homework due again?
The chapter 6 homework, I believe the document I just pulled out said December 2nd.
Okay,
December 2nd is
next week, Wednesday.
and so try to get them done by the 30th so that if you have questions on them, we can clear them up last time. All right?
Okay, thank you.
Okay. Anything else that I can do for anybody else? No? So shall we call it a night? If you have any problems with anything, please feel free to email me or stop by my office hours. And if I don't hear from you, have a wonderful Thanksgiving. And I think the advice that you always have to give for Thanksgiving is don't eat too much, right? So have a good one, everybody. Bye-bye.
Bye. Have a happy Thanksgiving.
You too. Mackenzie, what can I do for you?
Nothing. I'm okay. I was just busy taking the test. Sorry.
Okay, all right. We'll talk to you later. Bye-bye.
Thank you. Bye.